Okay. All right. So I'm going to go to top responses and let's see whether that changes anything. Okay, great. So can we explain noisy data again? What does a joint generated by a joint distribution, what does the noisy target function mean? Okay, so let's see. I can't do what I did last time, which is to star it. Okay, so a noisy data just means in the instances that we have. Let me put this up, okay? So let's say I have a vector, okay? And I have a class value. Okay, this is my y and this is my x. Okay, when we have noise that deals with the class label, this is called noisy target, right? Because this is my target value. It's perturbed in some way. So if you can think in regression, I have a real value output. Maybe that actual value that I observe has some error. For example, every time we use GPS, right? It doesn't give us a precise location, right? Maybe you play Pokemon Go or something, okay? So you have to wander around until the phone registers that you're in the correct place to find something, okay? So that type of measurement error in my target function, like if my target is where am I, okay, would be considered noisy target, okay? When we talk about noisy data, that means it's over here, right? That means our X value somehow is off, right? So it could be any component. Let's say, for example, this one here, let's say X3, okay? Maybe instead of, you know, te bing, I heard te sao or something like that, something hot instead of iced, okay? So I misheard something and then my data value that I recorded is wrong, okay? Now, of course, target and data can be interchanged, right? There's nothing special here to say that the target is the target and the data is the data, right? You can just think of this as some big vector, and then I can pick any one of these attributes and call this my y, right? And I can take everything else as my x, okay? So I can swap the idea of noisy target and noisy data around. It just depends on what type of thing that's of interest to me, okay? So I hope that clarifies that. What do we mean by generated by joint distribution? So when we go back to naive Bayes and Bayes assumption, right? When we have a probability value, okay, all right, when I say there's a probability, okay, I mean the joint probability of all of these things, because I got this data vector, right? I got this big vector here. It has my x and my y. So it's going to be my probability of x1, x2, da 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 da, xm, comma y, right? All of these things happen together for me to get out this particular row, right? So there's no way I can actually do what naive Bayes suggests, which is to cut apart all of these different features and take that joint probability and make it a series of conditional probabilities and multiply their products together. That's just not going to happen unless they really are conditionally independent. But most data that we gather is not going to be conditionally independent. There's going to be some correlation. The nice thing about naive Bayes is just it still works well in many cases, even though things are correlated with each other, okay? But you can think about what problems would come up. I mean, if we had, let's say, for example, an extreme example where I took the data for X1, whatever that thing is, okay, like maybe it's tea or coffee, and I used it for X2, X3, all the way to XM. So that basically all of these values show the same thing, okay? Then what does it mean? What happens in that case? And, you know, it's a vacuous case where we basically have one feature, but it's multiplied, you know, m times in my data matrix, okay? So you can do that thought experiment to try to answer that, okay? So I hope that clarified this question. So we'll go on to the next question. Okay, I didn't catch why L1 should be used instead of L2 for the example you gave in lecture of age versus gender. Okay, so L1 and L2 distance measures we'll cover a little bit more in the lectures for this week, okay, and later on as well. They're basically ways of measuring distance, right? So we have Manhattan distance, which is, again, something like a matrix. Oops, let me go back to my drawing. okay? So this is a little different from the ones that are in the image, okay? L1 just means for a particular dimension, I'm just going to take the absolute value of that dimension and the actual value for that dimension and add them up, okay? If I look at a distance of a point from another point, let's say here is the actual point that I want to find. This is my F, okay? And my point that I actually found through my hypothesis is over here. Okay, we can also equivalently call this, you know, uh, my approximated F, right? F hat, okay? That's another notation you'll see, okay? Then L1 is basically doing Manhattan distance, okay? Manhattan distance, if you've ever been to the US, right? Manhattan is a series of blocks. So it just means that I'm gonna calculate the distance by each dimension, my X dimension, right? Difference, okay, that's my delta here, and then my Y dimension difference, and then adding them together, okay? If I have L2, this means the normal case, right? We are just gonna say the direct distance, the Euclidean distance between 2 points in hypersphere, hyperdimensional space, okay? So those are the difference between L1 and L2. Now you're asking me, why should I use L1 versus L2, okay? Now, when you think about something like age and gender, okay? Let's say these are two parts of my features, right? X1, this is age, okay? And X2, this is gender, okay? And then X3, blah, 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 okay? If I use L2, right? And I'm gonna plot like we did before, okay? Maybe I'll use a different color. I'm sorry, blue's not gonna show up very well, okay? I plot gender and age, okay? Again, maybe we don't use gender, but you can take the idea from this, okay? And I say I have two completely semantically distinct features, all right? So gender is independent of age. It indicates something entirely different. But I take an L2 distance, okay, between my F and my H, and I measure distance like this, okay? What does it mean? That means somehow I'm trading off units of gender for units of age, right? Somehow I'm making them comparable because I'm using them on a distance measure, right? So normally we don't think about that, right? We think age is age, gender is gender. So let's keep these things separate, right? So I'm going to calculate a distance. I'm going to say, well, there's a difference between what I thought was the correct age and the right age, okay? And maybe I got my gender off too, okay? So I'm going to think of it like this, okay? So the bottom line is, and I think I said this in lecture, but just in case we're not clear, okay? L1 we use when we're comparing unlike features, okay? Unlike features, okay? Meaning that the things that we have put on a data matrix are different things, okay? So for example, in the credit approval application, right, we have salary, age, amount of time in your last residence, whether you're gainfully employed now, whether you have COVID-19 or whatever, okay? All of those different things, somehow they're not comparable, right? They're different objects. They're semantically distinct. So maybe we want to take a distance measure that aggregates all of those differences, you know, take the sum of them, but measure individually, right? So individual L1, okay? So that's the idea, okay? For L2, we're saying something different. We're saying these are, of course, then, for like features, right? Okay, like features means all of the things that are in my feature matrix, okay, my data matrix, represent the same thing. And we gave an example of this a couple times already. So if I have a picture of a cat, well, all of those 64 pixels or 1,044,100,000 pixels, they're pixels, okay? They're comparable things, okay? One pixel's difference and another pixel's difference is the same. So these are like objects. So it does make sense to do an L2 distance measure, right? So I can say, okay, R, G, and B, they're separated, but because these three dimensions are somehow representative of a higher order semantic of color, I'm just going to take the value between the color, okay? Meaning R, G, and V, R, G, and B, sorry, three-dimensional space, and I'm going to just take a distance measure between all this volume, okay? So I hope that helps you understand why we do this. This is a very useful question that I hope you will be able to get. So if you're all with me, give me a shout out on chat or put up your yes or your hands, a thumbs up, okay? So you understand the concept that's going on, okay? So if you have any questions about that, please let me know. Again, we'll try to go over it again if you guys have questions. Okay, so remember that when we go to your actual projects or when you're doing your notebooks, you need to use like features, okay, for L2, and for different features, you use L1. This is a default, okay? It's not to say it's always going to work better if you use one versus another. In fact, when it, L1 does well for for like features and L2 does well for unlike features, then, this should come as a shock or a surprise. And then you want to dive into your data more. Hey, why is it like that? How come it ends up that what the lecturer told me, what Min told me doesn't work out? Okay, oh, it's actually because the data processing that I did or my data set was acquired in a certain way. Okay, explain why the results are as they are. Okay, great. All right, let's go on. Okay, so I think I covered this part, the changes to the slides for Laplace smoothing. If you still got questions about that, I'll take that end of the lecture. Okay, what is the significance of accuracy for naive Bayes and KNN? Okay, how is accuracy computed for across the, and I think this is entire training set for both algorithms? Okay, so the way we calculate accuracy depends on the problem. Like we said in our cost functions part of lecture, which I haven't covered. Oops, sorry. Okay. Crap. Okay, let me try that again. Please don't freeze on me. Okay, we're back. Okay, so yeah. Accuracy, as we've talked about in the cost function part of the lecture, has to deal a lot with how we perceive different parts of the space to be important or not important. Okay, so when we think about accuracy, here it's very simple. We're just saying each individual item is worth a unit value, and you either get it right or you get it wrong. Okay, but like we introduced in the cost part of the lecture, sometimes different instances matter more, right? So for example, let's say you're trying to detect whether somebody is being hacked, okay? And so you get a number of data instances at different time points. And yes, hacked is a very rare occurrence, right? Most of the time it's smooth sailing, nothing's going on in the system. So you got millions and millions of instances of things as normal, okay? And you've got maybe 5 instances of somebody trying to hack, okay? Now you can tell already from our cost function lecture, right? Then it's not comparable. These two classes are different. If we actually try to build a system that's going to function very well, let's say with 99.99% accuracy, always get good accuracy, then it's very simple. I simply never tell you you're hacked, right? I mean, the 5 instances that you get hacked, hey, it's only 1 out of, 5 out of a million times, okay? But I can still tell you, hey, my system is really accurate, So if you want to confuse somebody like a venture capitalist who wants to give you money for your startup, just tell them your system is accurate, okay? Because they'll think, okay, well, you get 99% of the cases right. How bad could this startup be, okay? In fact, it's ludicrous, right? If you're building a system that's supposed to detect intrusion detection, you never classify anything as an intrusion detection, you get 99% accuracy, okay? You're not doing any work. Right? So basically, we do need to make sure that we have a good understanding of the concept of accuracy, the concept of unequal costs, right? So different instances have different costs, okay? Certain normal instances may cost less, okay? Certain instances may cost a lot more, okay? You can think of it in coronavirus or any type of thing that where one class happens more frequently than another. Hint to all of you, that is the norm, okay? Most types of classification problems, there are classes that are going to appear a lot more than usual, and often those cases are not something that we care about. Okay, we care about the exception cases, the ones that are the rare diamonds, you know, the perfect student or the flunking student. Okay, all of these things are the cases of the outliers that we want to have some other type of procedure to work on. Okay, so I hope that solves that problem. Okay, for naive Bayes and KNN, it's not specific to how we count. Okay, all machine learning algorithms, okay, when they're supervised, you can calculate an accuracy if you have the output, right? So you need a Y value, you need an actual answer for a test instance or a training instance to calculate accuracy. Okay, so it's not a specific question of you know, whether we're talking about naive Bayes or KNN or neural networks or decision tree. Okay, accuracy is counted the same way. And again, there's one difference that we do want to make clear if you weren't here for the beginning of the lecture, okay, which is, I think, in the post part. I think it's this week's lecture, sorry, so I won't cover it today. But this idea that of the training and test costs, when we're talking about cost function. Oh, we did do cost functions. Okay, let's see. I remember now. Yeah, it's right here. Okay. So let's go to that one. Okay. Yeah, okay. This is the slide that I wanted. This confuses quite a number of you, so I wanted to go over this. Okay. So I hope you guys are all clear about this part, okay? Why we get this value, right? This is just saying that I have some cost function, okay, which we're going to denote capital J for the overall cost. And we're going to use this little j to indicate a point-wise cost. That means for a particular point or data instance, how well or how badly did I do, okay? And so in machine learning, we're very kiasu, okay? We only worry about when we do poorly. We don't care, we don't even like clap ourselves on the back when we're doing well, okay? We just measure loss. So when things are doing well, you get zero loss, right? If you're doing badly, you get negative, you know, a positive loss, meaning that you're not doing so well. So you're trying to minimize your loss, okay? So that only happens when these two values don't equal each other, right? So they're off by something. Then we're going to declare a positive value for j. And then because we said we're going to do a point-wise cost, we're going to sum up all together and then take an average, right? And so some of you answered this in the comments, and I hope all of you got this, why this is the case, that we need a sum versus an average. Everyone good with that? You guys figured it out on your own? Some people say yes, no. Okay, so why don't we use a sum instead of an average? Okay, so a simple reason for that. So Christian, it's basically because when we have unequal sized data sets, okay? Imagine I have a data set of 1,000 training instances and I have another data set of 1,000,000 training instances, right? So if I don't average them, then of course it's much more likely that the data set with 1,000,000 training instances will have an overall higher cost, right? Maybe I'd prefer in that case to train on a smaller data set because I can minimize cost that way, right? So that's not what we want. We want the case where we can understand why we are doing well, okay? So it should be over the actual data instances that I have in my training set, okay? Now, that's sort of a simple definition. Like I said before, we might care about certain instances more than others. So this formulation that I put here is sort of like our basic, right? It's exactly the same as what we did in smoothing, which is saying uniform prior. Every instance is equally important. You know, it could be, you know, the president or, you know, a farmer or a professor or a student. It doesn't matter. Each individual is equally important. Okay, that's what we mean by this type of analogy. Okay, when we don't believe that, okay, for whatever reason, then we will need to think harder about how we structure our costs. Okay, and that requires knowing your data, right? Because if you don't know your data, well, you don't understand the different classes and why they're important, then you have no choice. You're just going to assume uniformity. Okay, So this part bothers a couple people, right? They're like, okay, what is this expectation thing sitting there for? Okay, I understand this part. Okay, I understand this red part. Okay, that I'm taking an individual instance and I'm computing a distance between that. And if it's far away, it's worse. If it's closer, I have less loss, it's better. Okay, but what does this expectation X mean? Okay, and that again has to deal with the fact that certain data instances may be more common than others, right? So if they're more common, then the expected X that you would get would be more frequent, right? So that means the more common cases should be counted more towards the test performance, right? So this is basically saying what's the probable X, right? So probable X. Okay, and then saying, well, because not all data instances happen equally, then I need to think about that. Okay, but again, this plays a little bit counterintuitive to what I said earlier, right? Which is that sometimes in machine learning we care about rare instances much more. Okay, like COVID-19 or intrusion detection or scam fraud or internet trolls. Okay, most social media, most games, most credit applications. Most cats look like cats, okay? They're all normal, right? But there are some cases in which they're not. And therefore, we may want to put more emphasis in that. So this is just, again, a very simple assumption to just say, the data instances that happen more often, we want to count them more towards our expected test performance. Okay, again, you'll see this J written in a lot of papers as a curly L for loss, okay? But in our lecture notes, we use J, so you should be comfortable with seeing both formulations. Okay, great. Let's go back. Okay. So we can go through these again if you need to. I hope I answered this question for you in the modifies Laplace moving example. How do we get P of yes equals 10/16? So I'm not going to answer that now. Okay. Okay, let's do another one. So this one, okay. Couldn't understand the standard deviation part growing slowly for cursive dimensionality. That's a nice one. So let's find that part. I think that's in post. Okay, let's go there. Okay, so KNN and a lot of algorithms have this problem, okay? And whenever we come up with a distance measure, okay, and we think of L1 or L2 or any other type of a norm, okay, we will have this problem, okay? Because when we go to high dimensions, and a lot of data sets that you will deal with are actually high dimensional, like again, think of pictures, right? If you're trying to classify a picture, there are, so many pixels, each of them is a dimension, right? And either you have to find some way of mapping that into a smaller dimensional space, or you use the entire Ross feature space of, let's say, 1,444,000 pixels, okay? And what happens is, again, as it says as a summary here, right? The number of points needed to make the type of distance calculation useful depends on the density of the data points in that space, okay? So you have a very rarefied field of a very high dimensional space, then, these points are basically all over the space, but they're not at the same density that would allow distance measures to work well, okay? And the easy thing to see why that's a problem is that when you blow up into high dimensional space, okay, the distance between points becomes very similar to each other. And you're thinking, how could that be the case? I mean, you're taking a random distribution, right? So how could it be very similar to each other? There should be some points that are closer and some places that are farther apart. I mean, that's what random means, right? And actually, that's not true. It's not true at all, okay? And so we can take a look why, okay? So for example, when we go to a single dimensional space, like on the left side, let's just imagine we section it up into 5 compartments, okay? So we've already done that here, right? Okay, let's do it easier. Let's just put 3 compartments, okay? front, okay, what's going on? Why am I annotating like that? Okay, middle and end. Okay, so I have 1/3, 1/3, and 1/3. Okay, so you know, 1/3 of it is in the middle. Okay, and then 2/3 on the end. Right. When I use this same type of way to take apart a square, then what do I get? Right. And so what's happening is you see the middle is shrinking proportion-wise. How much is in my middle space now? Only 1/9, right? I moved from 1/3 to 1/9, right? And when I move to 3 dimensions, it'll be 1/27, okay? So what this means is if I take a random distribution of points, more and more of the points are scattered on the outside boundary. They're no longer in the center, okay? And you can divide this up into more parts, right? So that means if you take a look at a very high dimensional space, like 100, okay, dimensions, that most of the points are going to be on the edge, very close to the edge of this 100 dimensional hypercube, okay? So all of those points on the edge, they're pretty much far away from everything, okay? Because, you know, being close to one edge or one face means that they're equally distant or very far apart from each other. So if you can imagine that in a very high dimensional space, when we run our learning algorithm, okay, or our predictions, right? What we end up with things that are just very far apart, okay? And even though we can still calculate a distance, okay, we can say that one point is actually closer to another, that difference becomes very indistinguishable, right? So if you can think, okay, if I think of 2 points really far away in different directions, it's, yeah, I can calculate which one is closer, but which one clusters to me doesn't seem to make a lot of sense anymore, right? So you have sort of arbitrary groupings of clusters where the clusters are just because 2 points are a little bit close to each other, but their standard deviations are roughly the same, okay? So I hope that solves the problem. And if you've gone through the unit hypercube simulation, there's a very good understanding of that. You can also look at one of my favorite YouTubers output, which is Free Blue, One Brown. They have a particular video, I'll try to put it up later, about how to visualize this idea in high dimensions. Okay, so they actually have a nice video about that. Okay, so I think I've addressed that. Okay, let's take this out of the way. Okay. Okay, this function of f of x equals e expectation of y given x plus noise of y and then f of x. Okay, so let's take a look at that. I don't remember which slide that's on, so you have to bear with me. Okay, this is basically this idea of having the actual function. Okay, so we can think of this as the true, sorry. Let me see what I can drag this back. Okay. What I can do is think about the true value, okay? This is my true value of f, okay? But then I'm observing this f instead, okay? This is not my true value. This is my f value with noise. So this is my true f, okay? And then I have some noise, right? My noise is the actual value minus the true value. So this is my true value. I subtract that, and then I have my noise term. So I actually see, you know, a noisy target, okay? A noisy target, this f over here, but it's composed of my actual expected true value of f plus a noise term. Okay, so that noise term is what we're analyzing here, right? It's the actual y minus the actual value, and this will be my noise, okay? All right. So if I answered most of your questions, I hope that's good. Let's see, I'm just gonna go back up to the top and make sure that we covered everything. So we talked about noisy data, so I'm gonna resolve that, okay? We talked about, okay, I haven't touched that. I think I talked to you about this, okay? I talked to you about changes in the slides for Laplace. And I think I covered this with you already. It's basically that for each value of f, of p, sorry, each value of f, right, are y values, okay, I'm going to add one. So originally I had only p of yes and p of no. So I'm going to add one observation to p of yes and add one observation to p of no. And then I will get 10 out of 16, right? Because the 16 comes from the 14, okay, comes from the 14, but I had to add one for the yes, and I had to add one for the no. Okay, the smooth values for the no. So I get 16 as the denominator. My yes comes from, again, okay, that I had 9 actual true observations, okay, plus I get one smoothed one, okay, that I added, okay. So that's why I get 10, okay. So that's why we get those results, okay. And we covered this one. I hope I covered this one with you, okay. And I covered just now this one as well. Okay, so let's go back up to the top. Can you explain the answer to question 1 of tutorial 2? Okay, I actually haven't looked at tutorial 2 yet. Yeah, let's see whether we can bring that up. Oh, tutorial 2. Okay, so we are going to go over this in tutorial this week. So actually, it's probably better that you listen to the results from your tutorial and then go through this first with them, okay? So there are 2 different questions here, part A and part B. And so I'm just gonna make sure I have the answer to that, okay? So give the sequence of S and G boundaries. This is basically stepping through the 2 algorithms, you know, finding S and G for the candidate elimination algorithm. So when we do that, basically you have 3 cases of positive examples, right, that you see here, right? So the positive, 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 and they're going to update what? Right, they're going to update our boundary for the general or the specific. Okay, and then the reverse will be true for the no example. When we have a no example, we have to reduce the generalization, right? Because not everything fits in our generalization space. So we're going to move G, right? And for these other ones, we're going to move S, right? So we have to cover all of the other cases there, right? So it just means stepping through this and giving this as an example. So I'm not going to cover this because, again, your tutorials will cover it. And you will get a solution key for it that will explain it. So if you're not clear after the solution, then come and ask again. I'm sorry about that, but I don't want to repeat what we're going to go over anyways. Okay, so although the final version space will be the same regardless of the sequence, right? Sometimes in the intermediate stage, we might get some differences. Okay, so the search space might be different. And that means, you know, in certain cases, we care about optimization, right? We don't want to use up too much space or use up too much time. So then you can think, what is an appropriate thing to do? Should I get all of the general instances first, or do I want to interleave them? What would make the most sense to make the version space that I have shrunk enough so that I don't have to do a lot of computation, okay? So that's the gist of this problem, okay? So I'm sorry, I'm not gonna answer all of that part of the question, but I hope I hit parts of what you were concerned about, okay? Okay, let's take this out, okay? So we'll hide that. In the loss function, what difference is there in using the mean versus the median? Okay, so there are many cases in which we care about the median, right? Which means that the most frequent piece of information, but maybe not the mean. And that is because sometimes we have outliers, right? So when we have outlier information, the median is not going to be affected, right? Because it's just basically what's the most common value, right? But because some of our outlier values could be very, very far off, like there could be a completely problematic measurement, right? There's always jokes on social media about I don't know, estimated transit times in airports or distance to a particular destination, even though it's right next to you. Maybe it takes you, the GPS routes you around the world or something like that. So many times we want to use the median instead, right? Or we need to do some appropriate pre-processing, right? Some appropriate pre-processing to get rid of certain pieces of information that we think are actually outliers, okay? So that's why we might prefer to use the median instead of the mean. Okay, but generally, many times we would actually want to change that out by doing some pre-processing to make sure we filter out outliers. We can carry out sometimes unsupervised learning to discard outliers. Okay, so if KNN has higher accuracy than NB, why wouldn't we use KNN all the time? Okay, so this is in the particular data set that we gave you in the notebook, KNN happens to do better, right, than naive Bayes. And naive Bayes here is sort of, it will work well on certain types of functions and not others. So KNN just happens, as we saw earlier in the slides, having a very complex boundary space, right? Dependent on how many points you have, okay? So a more complex space in some cases you can think of as being more, having more data, needing more data to represent it, okay? So again, if you think about a parameterized algorithm, a parametric algorithm, if I were to convert a KNN classifier into a parameterized algorithm, I would have to draw, you know, all of those line segments that you see in the Voronoi diagram, capture them as a part of the model and store them, okay? Compare that to naive Bayes. Naive Bayes is just saving a number of coefficients, basically one for each feature. So it's not using a lot of values, okay? So generally we'll see this later on when we get to bias and variance. The smaller the amount of assumptions that are being made, okay, by learning algorithm, the more likely it is to generalize, okay? And that means you can apply that algorithm and it will tend to perform okay, not very well, but okay on a large variety, because basically there's not a lot of things you can tune, okay? When you have a very complex function, let's say a KNN with many points, okay, if some of those parts are off, it won't do well and generalize on a new data set, okay, or something else, okay? We're going to discuss these in a lot more detail when we get to week 5, okay, next week, because this is a very key, important concept in machine learning, this idea of generalization by looking at the bias and variance of classifiers, okay? But the bottom line here is, if you ask this question, is actually higher accuracy depends on the data set. It depends on the features. It depends on your characterization, okay? So again, like we saw in concept learning, our whole point is that when we choose a particular learning algorithm, whether it is a concept learner, whether it's candidate elimination, or whether it's a KNN or naive Bayes, what we want to make sure is that it connects well with our intuition about why the output is the way it is. Why does the Y value get its value? What is responsible for it? Okay, so what is a hyperparameter? It means a parameter that tunes other parameters, okay? So hyperparameter in KNN, you can think of as some type of metaparameter that influences the workings of many other parts of KNN, okay? So you might think of it as a parameter, but here, there are other parameters that we include in KNN. So for example, how to break ties, okay? Whether we're going to use the distance from a point as a way of computing a sum or not, okay? So those are ways of weighting different values, okay? So these are all those parameter choices are affected by what setting of K you pick, okay? So in some cases, we would think of this as a hyperparameter because that particular choice influences the choice of many other more detailed parameter settings farther down. Okay, so that's what we mean by hyperparameter. Okay. All right. Okay, I don't think I think I've gone through most of these, but let's see how many do we have. Okay, I'll try to take a couple more before we break. Okay, so can you explain the part about choosing the cost function and how it affects the hypothesis? Okay, so it will affect the hypothesis because the way we weight whether or not a particular instance is important or not. Again, let's take COVID as an example, all right? If you miss somebody with COVID and you allow them into the community and it causes more spread, then that's a very poor outcome, right? We would much rather have declared somebody who's well, potential to be sick and quarantine them because it only affects one person. Whereas if we let somebody loose, it could eventually affect and kill many other people, right? So by weighting the cost function, it will change what type of hypothesis that we want, right? If we believe that, A candies and B candies are the same, there's no difference between them, we just want to count to accuracy. Like how often do I classify A candies well and B candies well? Okay, but in the case of COVID, I really, really want to catch somebody with COVID, at the cost of maybe making some people upset that they have to serve stay-at-home notices, even though they're not sick, okay? That's because I've changed my tolerance for making a mistake on somebody who actually has COVID. I don't want to make that mistake, okay? So in this case, maybe what I'll do is I'll change the classification boundary. Okay, so this week we talked about linear algorithms, right? So I'm just going to draw a picture of what that means from this, okay? So imagine, let's say I have a 2D space, okay? And I have some positive points and I have some negative points, right? Okay, negative, negative, positive, positive, okay? And I have something in the middle. I don't know what that is, right? So if I prefer to tell people that somebody has COVID, even though they don't, just for the sake of making sure I cover them, then maybe I would have drawn the classification boundary a little bit different, right? Maybe I would draw it something like this, okay? Meaning that everything on this side of the hyperplane is plus. So this one is right, this one is right. I have no idea whether this right, this one is right, and this one is right, okay? On the other hand, if I decided that, for another particular coronavirus, let's say the common flu, right? Okay, you get flu, you spread it to people, but it's not going to kill anyone for the most part, in Singapore at least. Then maybe I'd say that question mark over there, it's okay if you get it wrong, okay? Then maybe what I do is I just draw the classification hyperplane over here, right? I'd say, okay, I get this one right, 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 but I'm going to call this a negative class, right? Whereas before I would have called it a positive class. Okay, so it does affect your hypothesis because the weighting between whether you call something a false positive or a false negative, again, all these falses mean that there's a loss, right? Something was misclassified is dependent on what we want to guarantee. Okay, so I hope that answers that question. Okay, so I'm going to hide that. So I already did this, so I'm going to hide this as well. Objective function when choosing hyperparameter k, okay? So when we choose a hyperparameter, we basically need to make sure that we get good value for our choice, right? And when we get to regularization and validation, basically that's where we come into this play, right? Basically what we said before is that what we can do is we're going to take some part of our training data, okay, where we have answers, we're going to cut it off, we're going to save that, okay, for practice, right? What we're going to do is we're going to train our KNN function with different choices of hyperparameters, right? Our different choices of hyperparameters over here. And then on the held out training set, which I didn't get to look at, but which I have the answers for, I'm going to apply KNN and then see how well it does, okay? And if I do very well on it, maybe that's a good reason why I would choose that hyperparameter value, okay? So we also have to consider the possibility of underfitting and overfitting. So when we come to bias and variance, we'll talk about this a little bit. And also in our unsupervised learning algorithm, we often have a penalty for a hypothesis that's overly complex. Unfortunately, for the scope of this course, which is the introduction to machine learning, where we've incorporated some deep learning aspects, we don't have time to really introduce to you what mathematically we mean by complexity of a hypothesis. But there are ways of measuring that. So you may have heard of minimum description length, things of this sort, characterize how much data, okay, how much data we need to encode a representation. And the more data we need to incorporate in the representation, the more complex that hypothesis is. Okay, I think I covered this, so if you still don't understand, please let me know. Okay, features are not conditionally independent. Does that mean naive Bayes is not a good model to use? Generally, yes. Okay, generally we don't want to use naive Bayes when things are not conditionally independent. What happens if we still use it? Okay, so I gave you some ideas about why that's something you can try. You can try a thought experiment where all of the data, okay, all of the individual X's are actually replicants of a single data column, okay? And what does this mean? Okay. Okay, so I covered this one as well about L2, L1, and normalizing I also talked about, okay? And so I think I covered this. If you're still not sure, ask again. I'm sorry, maybe you had heard it or came in late, okay? Okay. Do many ML algorithms support cost functions? Yes. Most ML algorithms do have some idea about why certain instances are more important than others. And in fact, you can simulate this, right? You can say, oh, if I believe that test case number 2 is twice as important as test case number 1, I can simply replicate it, right? I can say, oh, now let's just pretend we have 2 cases of test case 2 and 1 case of test case 1, and I want to optimize the overall accuracy, right? So if I get all 3 right, that's great. If I get 2 right by getting the replicated cases right, that's also not so bad. It's just getting 1 right, okay? So there are many ways that we can play with cost functions to induce something that's more sensitive to an actual value, okay? So as long as we can parameterize what it means to be costing, okay, and later on you're going to see from the gradient descent and the stochastic gradient descent, what we want from a cost function is it needs to be differentiable, right? It needs to be differentiable so that we can find a gradient. The gradient is going to allow us to find a stationary point, and that's going to be an optimum or you know, a minimum or a maximum, okay? And that's going to help us decide what the right parameter values are, okay? Okay, stochastic gradient descent, different from batch. We're going to talk about it this week in lecture. So you've watched it already, I guess. Okay, I will cover that next week in week 05's Ask Me Anything. So if you're not sure and you want to find out in the meantime, please ask it on the forum. I think if you watch these two or you watch the stochastic gradient descent part and watch carefully, maybe you'll get the idea. There's actually no difference, okay? The big difference is in running time and the fact that stochastic gradient descent, basically, when you do it in the limit, it's exactly the same as batch gradient descent, but it's a hell of a lot faster, okay? So this is why we always use stochastic gradient descent, okay? Almost always. There's only a minority of cases when you have very little data that it probably doesn't make sense to use a stochastic algorithm, okay? Will the lecture for last Monday be uploaded? I will try to get to it. Yeah, I will try to do that. I didn't know there was so much demand for it, so I will put that up. It's not going to be edited, so I think, again, it's probably more useful to ask on the forum, and then where we have time, we'll put answers to it. Sometimes I think it's a lot easier for me and for most of you not to watch video and then try to scrub it, because you know, these videos are not very easy to scrub anyways, but to actually see it in a text form. Okay, so I already covered this part about not needing to scale our data when we actually know the data well enough and we think that certain features of the data should not be hidden through normalization. Okay, so sometimes it's a bad idea to normalize data because the data as it is indicates what we want to show. Okay, so this is actually supposed to be 411. So if you see the updated slides, this is corrected already. Okay. Nearest neighbor is said to be non-parametric. Is there any significance of it being parametric or not? Yes, definitely. Parametric means that you have a model. You have a series of parameters that represents the model. If you don't have a parametric algorithm, it means you need to carry around all the data. Okay, all the data has to be present for you to make a decision, or else you have to find some way of throwing away some part of the data that's not important. Okay, we'll see that in SVMs in next week if we get around to teaching that. Okay, so the important part is that with a parametric algorithm, you're somehow getting a mental representation of what is the decision boundary. Okay, so that's oftentimes more compact. Okay, again, if you think of a linear hyperplane that we introduced this week in the linear lecture, right? Just knowing a y equals mx plus b, and whether you have 1,000,000 data points, 500 data points, or 1,000,000,000 data points doesn't matter, right? You just need to carry around two pieces of information. What's my slope? What's my intercept? That's it, right? And then we're all done. Does a smoother surface from larger KNN help generalization, or is more for visual? So again, this depends on your data, right? If we think we have noisy targets and we think there's mislabeling in the data, or a noise that comes from the data not being measured correctly, meaning noise in our X, then a larger K generally helps for generalization, right? Because you get smoother boundaries, okay? And one particular instance doesn't decide everything, okay? So you can think about it from a democratic point of view, right? When you have a large K, you're getting votes from many different individuals about what to be is done. And then it's very hard to be agile, right? You can't make a sudden decision and change from one class to another, okay? It has to be a vote of many, many individual instances that decides, okay? So it really depends on the trade-off between whether you think the collective is right, okay, meaning that most of the instances know what they're doing, or you think the individual is right. So there may be cases in which a data set that there are certain instances that are just very important. Okay, again, we can think about the case where there are outlier detection, then you definitely don't want a large K because all of the general cases will tell you that it's a normal thing. Okay, so we don't want to do that. Can the pre-slides for this week be re-uploaded? There's a gray overlay on the slides. I'll take a look at that, and if it's still there, I will definitely do that. Okay, so I've come to the end of our Ask Me Anything. So if you have additional questions, please help us unmute, turn on your video camera, and I can take a couple more questions for now. All right. So I see some of your comments. Yeah, I think we've done this part before where you guys are asking about hacking and cost functions. Yes, so that's very much a big problem that we have. Okay, that we want to make sure we're using the right cost function to measure performance. If we use the wrong one, we can get ourselves into a lot of trouble because we can emphasize or de-emphasize particular data instances that we really care about. Okay, so it's absolutely critical you understand that point. Okay, so if there are no more questions, I'm going to finish here. If you've got anything else, put your hand up. Otherwise, I'll just wait a couple seconds here and let you tell me anything else.
Thanks, Prof.
Thank you very much for attending. Sorry it took so long. Okay, I'll see you guys all next week. Take care, stay safe. Bye now.